Everyone, welcome to the Mogobar Show. My name is Gabe. With me, I have Dan Wilkins. Dan is a research scientist at the Kavli Institute for Particle Astrophysics and Cosmology at Stanford University. The reason that I asked Dan to join me today is because I came across an article in Live Science a few weeks ago where they discussed Einstein's theories once again being proven correct. Honestly, I'm amazed when I came across this because this was something back in 1915, he came up with the theory of relativity, or rather not came up with it, but released it to the world. And this is interesting. Over 100 years later, he's still being proven correct. What is it? And for those that don't know, the theory, his basic theory of relativity is the fabric of space-time, how light bends to the curvature of whatever is in front of it. So I'm attracted to this because I'm a sci-fi geek. I'm a science geek. I love reading about things like this. And if you can hear me now, if you're listening to this, then you know I have no idea what I'm talking about. So Dan, please take it away. How did this come to be?
So we were looking at a supermassive black hole. In particular, we were looking at a supermassive black hole in another galaxy that is swallowing a lot of gas at quite a high rate. So there's this big amount of gas falling into a black hole in the middle of a galaxy. And when that happens, the gas gets superheated. So this gas in its final seconds before it falls into the black hole actually powers some of the brightest things that we can see in the whole universe. So we were looking at the X-rays, actually. So X-rays are a high energy form of light, but we were looking at the X-rays that are emitted by this gas in its final moments as it falls into a black hole.
That's amazing. The galaxy in question is the Zwicky galaxy, which, 1,800 million light years away, if I remember correctly. First off, I'm fascinated by the name and who came up with it and why they came up with it, but that's a conversation for another day, probably. Really, I want to know, why were you looking at this galaxy? Why were you studying the X-rays of this galaxy that's so far away? What are the implications? What do you hope to learn from this?
So it turns out that this gas falling into black holes actually powers some of the brightest things that we can see in the whole universe. So that's kind of crazy when you think about it, because when people think about black holes, they think about these things that nothing can escape from, no light can escape. So it's kind of weird to think that you can have a black hole powering the brightest things that we see in the whole universe. Like if all the light's falling into the black hole and nothing can get out, how can it be the brightest thing? The answer is that it's not actually the light coming out of the black hole. It's the gas around the black hole falling into the black hole that is shining so brightly. And we're seeing the light that gets emitted in sort of the final moments of this gas before it's forever lost inside. And we really just want to understand how these objects work. How is it gas falling into a black hole is able to power the brightest light sources in the universe? And also understand the role that these black holes played in helping the galaxies form.
Okay, so we study this. We learn more about this. How does this impact humanity? What are the benefits? What benefits are there to humanity going forward in the sciences? And again, I'm a sci-fi geek. I'm looking at space travel. Everybody is obviously aware of Blue Origin, SpaceX, Axiom. They're all over the news. I grew up in Star Trek: The Next Generation era of the 80s, and I realized that this isn't that. I get that. But what are the implications for humanity? How does understanding these gases and the forming of the universe help us be better or help us accomplish more?
So I think there are two sides to that. So the first one, I think that it really goes to the heart of what it is to be human, that we are sort of conscious beings and we are able to explore the world around us and the place we have in it. And so I think it just goes really to the heart of curiosity to answer that ultimate question. How does the universe work and how did we get here? And it turns out that these black holes, because they release so much energy, the black hole in the center of a galaxy actually plays a really important role in guiding the formation of the galaxy around it. It stops galaxies getting too big. It makes sure that they form sort of the, I guess for want of a better word, the right number of stars. So understanding what's going on around black hole also is an important step in understanding how the Milky Way got here, how the sun got here, and how really the universe that we live in came to be. And on our way to this journey, we end up stumbling across actually some technology that could be really useful. So we need to develop cameras that are able to sense X-rays coming from the far side of the universe. And the development of things like detector and camera technology has a lot of applications. So, I mean, the X-ray detectors that we're using can also be useful in sort of medical imaging and in security scanners and things like that. And other techniques that have been developed for exploring the universe, particularly exploring the universe with radio waves, is actually the technology that led to Wi-Fi that we all use today. So by answering these really hard problems, it makes us develop new technologies that actually find other uses here on Earth as well.
So in other words, the next time we're at Starbucks, we need to thank you, because if not for you guys, we wouldn't be able to connect our phones and our laptops. That's awesome. I love that. I want to get back to what you were saying, a supermassive black hole. Black holes, in my layman and uneducated understanding of them, are massive enough to begin with. What is a supermassive black hole compared to a regular black hole?
So when we look at black holes, there are two types of black holes that we see in our universe. The first ones that I guess are the regular black holes. Astronomers call them stellar mass black holes. These are black holes that they weigh a few times more than the sun, maybe 10 times as much as the sun. And these black holes form when massive stars come to the ends of their lives. So the really big stars, when they run out of fuel, they do a number of things, and eventually they'll blow up in a supernova explosion. And what's left collapses under its own weight, and that can form one of these small black holes, these regular black holes. And we find these scattered all through the galaxy. Anywhere you find stars being born and stars dying in galaxies, you can find stellar mass black holes. But then the supermassive black holes are the black holes that are a whole different scale. Instead of talking maybe 10 times the mass of the sun, we're talking 1,000,000 times the mass of the sun, even 1 billion or even 10 billion times the mass of the sun. And we actually find a supermassive black hole in the center of pretty much every galaxy in our universe. So the Milky Way, our own galaxy, we have our own supermassive black hole sitting right in the center of the galaxy. And pretty much any other galaxy we'll look at with our telescopes, maybe not some of the small dwarf galaxies, but pretty much every galaxy we look at, we believe there's a supermassive black hole sat right in the center of the galaxy.
So is humanity in danger of being swallowed by one of these supermassive black holes that nothing can escape from? Is that what I'm hearing? Like, is there a risk that of the black hole potentially expanding at some point and just devouring the entire galaxy and all of humanity with it? Or will we continue to exist in this black hole? Have we already been swallowed and just don't know it?
Lucky for us, the black hole in the middle of our galaxy shouldn't be any threat to us at all. So the thing with a black hole is if you're a long way away from it, I mean, the black hole in the center of our galaxy is sort of 50,000 light years away. When you're a long way from a black hole, it has a force of gravity that pulls things towards it, but that's just regular gravity, like we're used to here on Earth. So the gravity is holding us down on the planet. And we also feel the gravity of the sun as well. We're being pulled towards the sun, and that's what keeps the Earth traveling around the sun year after year in its orbit. We're not being pulled into the sun. It just has enough gravity to hold us in orbit. And it's exactly the same with a black hole. If you're a long way from it, it has regular gravity. So there's a pull towards it. But the thing with a black hole is it's when you get really close to it that things start to get weird. A black hole is formed essentially when you end up with something, whether it's a dying star or it's some big cloud of gas. There's just so much stuff in one place that it has this huge force of gravity pulling it together. And eventually, if you have enough stuff, the gravity gets so strong that nothing is able to push back. So whatever you've got, the dying star or the cloud of gas in the center of the galaxy, just ends up collapsing under its own weight. And it collapses and collapses and collapses. It's just getting pulled together by that gravity. And eventually it gets pulled together so much that it's been crushed into such a small volume that the gravity at its surface gets really strong. And that's when you form a black hole. It's when you get close enough to that black hole that the force of gravity is so strong that nothing can escape it. So long as you stay a nice safe distance away, you're fine. But if you get too close to it, nothing will protect you from its gravity and it'll pull you in, and then there's no way out again.
That's fascinating. I've read about black holes in science fiction. I've read about them in, science literature. Just for my sheer curiosity, not that I had a stake in it. I couldn't understand fully what I was reading. I've never actually understood a black hole until now. When you explained it, I'm like, that sort of actually makes sense. What's next for you? What's this discovery? You've been here. Has it refocused you? Has it repurposed your thoughts about everything that you've been studying? Where do you go to next? What are you going to do now?
So I think that there's two real sides to our studies here. I mean, the first one is we really want to be able to see what's happening just outside a black hole, to understand how the gas falling in is powering such bright light sources. And then the other thing is, so Einstein's theory of gravity, called general relativity, predicts that lots of weird and wonderful things happen when gravity gets really strong and when you get close to black holes. And my research really tries to combine those two things. We're always looking for new ways to map out what's going on around a black hole and understand exactly what happens to that gas in its final moments. And I'm always looking for new ways to try and see these weird and wonderful things that Einstein predicted. And that's essentially what we saw with this light being bent around the black hole. But there was so much that we saw in these observations. I mean, it all started when all of a sudden, while we were looking at it, this black hole started emitting these really bright flashes of X-rays. It was sort of shining along, we were looking at it, and all of a sudden it started getting much brighter really quickly. So it lets off these bright flashes. And these bright flashes are something that had been interesting to my colleagues and I for a while, because we realized probably about 10 years or so ago now that when you get flashes of X-rays around black holes, you can then see the echoes of those X-rays off of the gas that's falling in. So you get the flash of light first, and then you see the echo of that light off of the gas falling into the black hole. Now, these black holes are so small and far away that we can't actually take a photograph or an image of this gas. But by looking for these echoes, we can actually start to reconstruct a photograph, reconstruct an image of what's happening just outside the black hole. And what was really interesting here is that we realized that we saw the bright flash of X-rays and we saw the echo. But then we saw, as the flash was fading away, we saw a second echo coming much later. And we realized that this is the echo coming from the gas that's just behind the black hole from our point of view. So you can imagine there's a black hole here, and there's gas all around it, and some of that gas is just on the far side. And this is the echo of the flash of X-rays off of that bit of gas that's behind the black hole. Now, that bit of gas should be hidden to us, because any light that tries to go through the black hole can't. It'll go into the black hole and then it can't come out again. But the reason we can see this is because the black hole is bending space around it. And the light doesn't have to travel through the black hole to get to us. It's able to go around the black hole. And that was our big discovery here, is that we kind of figured that there should, anytime we look at echoes from around a black hole, we should be able, some of that echo should be coming from behind the black hole. But we never thought we'd be able to see that echo directly. We just thought it would be lost into all the other light, into the original flare and into the other echoes from all the gas in front of us that are much brighter. But because these flares were so bright, we were actually able to pick out that extra echo that came later. And that echo appears in exactly the way that Einstein's theory predicts it does. I mean, this isn't something that's completely new. I mean, Einstein himself actually was able to observe that, just like he predicted, light is bent around massive objects. Einstein, along with the astronomer Arthur Eddington, observed that, just as Einstein had predicted, the sun is able to bend light around itself, ever so slightly, because the sun is nowhere near as dense as a black hole. But they realized that if you're looking at stars that are behind the sun, they appear in the wrong place just because of the way the light gets bent. And we've been looking at massive galaxies in our universe, bending the light from galaxies far away for quite a number of years now. So this bending of light, as Einstein predicted, is nothing new. It's just now we're seeing it on this really extreme scale. We're seeing light that should be coming from all the way behind the black hole being bent all the way around the black hole so we can see it.
That's amazing. As someone who's constantly reading stuff, all I knew of Einstein was E equals mc squared. I think that's what most people in my position know. We don't always know all of the scientific stuff. But his theory of general relativity, the fact that over 100 years later, his theories are still being proven correctly or sought to be proven is utterly amazing. What is that like? What I mean is, again, the time, over 100 years later, here you are, basically sort of tied to a man who's considered to be the most famous or successful scientist of the 20th century. And I don't mean it as you're the one that's saying this, but I'm the one that's saying this because I came to know you or of you through my reading and research and how you were linked to this because of, Albert Einstein. And I just became enthralled by it. And I needed to know you. I needed to meet you. So it's fascinating to me. And sure, it doesn't help him to have these theories proven correct. He's long gone. What is the feeling like? Obviously, when a discovery like this comes up, there's always going to be people who are skeptical of a discovery. I read somewhere that scientists are the most skeptical breed of humans around, that they always, no matter how many times something's been proven, there's always the opposite opinion that until they discover it. What has that been like in the scientific community, in astrophysics? What's been the reception, the perception, the appreciation, or lack thereof?
I think it's been pretty amazing, actually. So I think to a lot of physicists and astronomers, it's not that Einstein was correct is the big deal here. It's that Einstein predicted a lot of things back in 1916 that are actually really difficult to go and prove. And I mean, you said that that scientists are a skeptical bunch. It's if you want to claim something new, if you want to change the sort of the zeitgeist for how we think the universe works, you can't just come up with a new idea that roughly explains things we see around us. You need to show that whatever theory you're proposing really is the only way to explain our universe. And the real way to do that is so kind of one of the rules of scientific exploration and discovery is your theory can't just reproduce things we already know. Because whenever you come up with a theory, you always have options and numbers you can tune and play around with. So you can always tune your theory to match things that we already know. The real test for a theory is to predict something that we haven't seen before. So then either the same scientists or another group of scientists can go out and they can do the experiment and they can find out if this prediction is correct. And that's exactly what Einstein did. I mean, he came up with this theory, and then a few years later, him and Arthur Eddington went and observed how light was bent around the sun, and that confirmed the theory. And general relativity, I mean, I think for scientists, I think one sort of activity that I think quite a lot of scientists like is to try and disprove Einstein. I mean, in particular, this comes in not so much looking at black holes and really strong gravity, but in the larger scales of our universe. We have a couple of challenges in understanding how our whole universe fits together. And there are phrases you might have come across: dark energy and dark matter. And these are things that we have to invoke to get Einstein's theory of gravity to work, to explain how the universe as a whole appears to behave. We see that gravity in massive galaxies is stronger than it should be from the number of stars that are there. So there must be some extra material in the galaxy that provides gravity that isn't shining, so we can't see it. And that's what we call dark matter. But sort of an alternative viewpoint to that is, okay, maybe there isn't extra stuff in a galaxy that we can't see. Maybe just the theory of gravity is wrong. So there are alternative theories of gravity that maybe do away with this need to put extra dark matter in. And then we also see that our universe is expanding, and it's not just expanding, but it's accelerating. It's getting quicker and quicker. And to do that, there needs to be some force pushing the universe apart. And this is something that we call dark energy. We have no idea what it is, but it's some sort of force that's pushing the universe apart. But sort of flip side to that is, okay, maybe there isn't a force pushing the universe apart. Maybe our understanding of gravity isn't correct when we look at the universe on the biggest scales. But with these new findings, what we can essentially do is we can say, we can limit some of those new theories that you might want to bring in to replace Einstein's theory of gravity, because we can say that even if you push gravity to its real extreme, we're literally just outside a black hole, and we're looking at how the light is being bent around the black hole. Gravity is still working in the way that general relativity says it should. So that means if you want to throw away general relativity and come up with something else to explain the expansion of the universe, you need to be really careful in doing that, because you need to still explain what we see around the black hole, is the thing there. But also going back to the sort of the reception in the astronomical community, I think actually one of the more exciting things for my colleagues and I isn't so much that we've sort of said that Einstein's right again. I mean, we know that light gets bent around massive objects, and we're just saying, okay, yes, it still gets bent in the same way around massive black holes. But I think for us, I think one of the really exciting things here is how we can use this new result. We're not just seeing that light gets bent around the back of a black hole, but in doing that, we've developed a new understanding and a new technique for seeing that echo in our measurements. And this is what's going to be really crucial in using these measurements of X-ray flares and X-ray echoes to reconstructing these pictures and these maps of what's happening literally just outside black holes.
Dan, I want to thank you. This has been so insightful, and I'm very grateful to you for taking the time to join me. I want to ask you one last question that has absolutely nothing to do with science. It's more of a fun question. Like I said before, I'm a sci-fi geek. I like to watch sci-fi movies. Do you watch sci-fi movies, and how do you feel when you watch them? Do you get upset when you see something, or that you hear them say something, or do you cringe and you'd be like, nah, that's not accurate?
So I'm going to say, I mean, I really enjoy watching sci-fi movies and sci-fi series. I mean, I'm a big fan of Star Trek. I mean, you mentioned that earlier. And I think that there's two sides to the fun in that. I mean, so one thing that's interesting about Star Trek is they don't necessarily hold to the laws of physics as we understand them, but they kind of come up with their own laws of physics and they're kind of consistent in that. So it's all kind of logical. And then when you have the other movies that just sort of completely get creative with the laws of physics, I mean, that's part of the fun of watching it, I think. I mean, we can enjoy the movie and then we can also enjoy sort of criticizing some of the science in
it. Dan, thank you so much. I really appreciate your time. I'm so grateful. I can't wait to see what else you guys come up with. This has just been absolutely fascinating. Thank you so much again. I appreciate your time so much.
Yeah, thank you.